Hi, my name is Rudian Windsor. I'm presenting our new paper, Self-Supervised Multi-Modal Alignment for Whole Body Medical Imaging. Our paper's main contributions are as follows. We propose a new self-supervised method of representation learning for medical images. This relies on matching different modality scans corresponding to the same subject via a cross-modal local correspondence search. We apply this framework to a large dataset of paired DEXA and MRI whole-body scans from the UK Biobank. Experiments show this approach to be highly successful at matching same-subject scans, vastly outperforming a conventional noise-contrastive estimation baseline. Finally, we show that the learned representations are useful for downstream tasks. In this case, we apply these representations to unsupervised registration in cases where conventional methods fail, and to cross-modal segmentation. We'll begin by discussing our new contrastive framework. The aim of our pre-training task is to match together DEXA and MRI scans which show the same subject. The panels here show scans corresponding to 4 unique subjects from our dataset. Can you match the DEXA above to the corresponding MRI below? If you wish to attempt this, please pause the video now. To solve this task, one must find unique and semantically meaningful features in each modality and match them together. This is the aim of our pre-training stage, to train networks that produce embeddings which encode what is unique about each scan, and this in turn could be clinically relevant. However, our method differs from conventional self-supervised frameworks like SimCLR in that instead of representing scans as a single global embedding vector, we instead represent them as a spatial feature map. To measure the similarity between the two feature maps, we correlate them using a standard convolution operation. In practice, this tells us the local similarity between the scans across a range of possible relative transforms. The maximal value of the resulting correlation map tells us the similarity between the scan pairs, and this is given to a standard noise contrastive estimation loss, which is used to train the encoders. Furthermore, the location of this maximal value tells us the relative transform at which the scans are most similar, and this can be interpreted as a simple registration between the two scans. Before discussing our results, let me introduce the dataset used. It consists of over 20,000 scan pairs from the UK Biobank, which we split into training, validation and testing datasets. We've made our code for downloading and pre-processing these scans publicly available, although it should be noted that to access this data, a UK Biobank registration is needed. The performance of our network at the scan matching task is encouraging. We compare to a contrastive baseline which encodes scans as a single embedding vector and report a significant improvement in performance. From over 2,000 possible options, our method can find the exact corresponding scan over 90% of the time, compared to 26% for the baseline. As an added benefit to our approach, we can calculate the similarity between spatial regions in both modalities. In turn, this allows us to determine correspondences between the two scans, which cannot be achieved by conventional shallow multimodal features like MIND or SIFT shown here. As a result of these correspondences, we can perform unsupervised registration between the scans. We propose 3 methods to do this, each of which improves on mutual information as a baseline. Thanks for showing interest. For more information on the contrastive framework and registration methods proposed, as well as experiments on segmenting MRI scans based on DEXA annotations, please read the paper. Our code is also publicly available using these links.